Hi, this presentation deals with cereal dilutions. What you're doing here is you typically have a sample. It may be a water sample, it could be a soil sample, it could be a food sample, it could be a sample from a patient. And what you want to do is find out how concentrated it is. By that I mean how many microorganisms are in it, and usually you record it. If it's a solid medium, you record it as how many microorganisms per gram. If it's liquid, how many microorganisms per milliliter. Now, in this lab, we are not looking at total microorganisms, so we'd be looking at bacteria. So how many bacteria per gram in the soil sample, or how many bacteria per milliliter of milk are in the sample. Oftentimes the original sample has an awful lot of microorganisms. You can't see them, but it's very, very concentrated. And so in order to get an accurate, correct count, you have to dilute that first sample down. And so for a cereal dilution, that's what you're going to do. You're going to dilute the sample down, and then you're going to put the diluted samples on a plate, and you will count the number of bacterial colonies that you see there. Something you must always remember is just an established rule, if you will, that on a petri dish, when you go to count the colonies, you only count between 30 and 300. What you will do is you're going to count those colonies between that range, and then you're going to relate that number, however many you came up, let's say 67. You're going to relate that number back to the original sample. How? By using your dilution factor. And you're going to be able to determine at least an estimate of how many bacteria were present there. So when you do the cereal dilution, we'll show you on the next slide how we do it. But the end result is that on petri dishes, if it's still very concentrated, and you oftentimes see this, that on certain dilutions where it hasn't been diluted out enough, you get solid growth on that plate. If it is completely covered, you don't see individual colonies. It's just a complete cover of bacteria. We call that a confluent growth or a confluent lawn. You can't count that. You may have some as you start to dilute out a little bit more. Somewhere, okay, it's not completely covered like this lawn, but there's over 300 colonies, so you don't count that. You might record it as TNTC, stands for too numerous to count. It just means there's over 300. Ignore it. You can't relate that accurately back to the original sample. The usable count, as we said previously, will be between 30 and 300. Now, if there's fewer than 300 colonies on the plate, you're going to ignore that in your calculations as well. You would record it as TFTC, which is too few to count. So how do you do the dilution? You have your original sample. Like I said, this could be maybe soil sample, it could be a food sample, water sample, whatever it is. So it could be solid or liquid. You have that original sample. What you do, in this case I'm showing with a liquid. If it was a solid, you would measure a gram of soil. If it's liquid, you're measuring 1 milliliter. You take that from the original sample and you put it into a test tube or into a flask. In this case I'm showing that it has, in this A container, it already has 9 milliliters of sterile water in it. So you would now say this original sample, we compare everything back to it, is a 1 to 10 dilution in sample A. So sample A is diluted 1 to 10 as compared to the original. How do I get the 1 to 10? The 1 comes from over here. How much did you put in? You put 1 in. What's the total volume now? You had 1 mil here that you placed into the 9 mils, so the total is 10. So the 1 is how much did you put in, and then the 10 is what is the total final volume. Now, Oftentimes we do a serial dilution, meaning you do several dilutions successively in a row. So you go from the original to A to B, B to C, C to D. It depends on what you're doing as to how far out you go. Sometimes it's a guessing game. Well, I'm not sure how concentrated the sample is. If it's really, really concentrated, lots of bacteria in it, you're going to probably dilute out more because you're trying to hit that range of 30 to 300. You don't know. That's why you're trying to test to see what's in there. So yes, it does become a guessing game sometimes. After a while, you kind of get an idea as to how far you need to go. So in this sample, now what we want to do is we want to take sample A and dilute it. So you take 1 ml out of this sample A. We're taking 1 ml out and we are placing it in sample B. B has 9.0 milliliters in it, just like A did. So originally it has sterile water, 9.0 mils of it. You're placing 1 ml into it. That would be a 1 to 10 dilution again, because you're taking 1 ml, your total volume is 10. So B is a 1 to 10 dilution as compared to A. But we're not comparing to A, we're comparing back to the original sample. So the way you do this is now multiply. So we already said that A is a 1 to 10 dilution. We said B is a 1 to 10 dilution from A, so you just multiply them together. So you would say 1 times 1 is 1, 10 times 10 is 100. So B is diluted 1 to 100 as compared to that original sample. So if you were to take a sample from B and plate it on a petri dish, and there's other videos that explain how to do this and how to do the calculations and all. But if you took a sample and you plated it and it fell within, the number of colonies fell within 30 to 300, you would use that sample. And when I say you relate the usable number back to the dilution factor, this is the dilution factor. So let's say you did take a sample from here. You took 1 milliliter, you put it on a petri dish, and let's just say you had 35 colonies. Well, 35 is greater than 30, so you would count it. So you would take that 35 that you got, that's the number of colonies, you would multiply 35 times 100, because that's the dilution factor. And you get 3,500 bacteria per milliliter. That's the concentration of it in this original container. So like I say, you'll find that for several situations, you may be working with a very concentrated sample. It can be solid, it can be liquid, whatever it is, and you have to dilute it out to try to get a number. Why is it so important to know what the concentration or what the number of bacteria per gram or per mil? Let's say you're working with a water sample. Is it safe to drink? Depending on the numbers, you might say, okay, it's safe to drink, numbers are really low. Or you might say, ooh, those numbers are pretty high. Maybe it should not be described as being allowed for human consumption. Maybe we can use the water to water a golf course, but you can't drink it. So that's why we need to often know to see whether things are safe to consume, safe to use, is what is the concentration of the bacteria. So the serial dilution is a way of trying to get that number.